Testing, testing, 1, 2, 3. Hi everyone, this is Orijuela, and this is your lab video for lab number 6, where we use everything that we learned in the previous labs in order to construct our MIPS data path, okay? So, ideally, you shouldn't be watching this video until after we've already covered chapter 4 material, where we go over the processor. But yeah, so what we're going to do in this video is that we're going to take all the material that we learned from the previous labs and use that to construct this MIPS data path. Now, I know that this circuit here looks big and confusing, but don't let that intimidate you. I'm going to walk you through how each component of this circuit works one by one. Okay? So when it comes to this circuit here, I actually provide for you all of the code. So you're going to need 7.v files in total. And each of these Verilog files contains a module that you're going to need in order to construct the MIPS data path. Okay, so there's going to be a mux.v, an incur.v, a mem.v, pcmod.v, ifid.v, fetch.v, and then pipeline.v. This is kind of like your test bench. Okay, so if you scroll down in this lab manual, I actually provide all the code for you. So I'm giving it to you in the form of pictures, and the reason why is because the reason I'm giving it to you in the form of pictures and instead of text is because I actually want you to go through and type all of this code yourself, because actually typing the code gives you a better idea of what exactly the code is doing. Okay, so here's the code one by one, as you can see. And then lastly, yeah, so ifetch.v is kind of brings it together, and then pipeline.v is your test bench. Okay, so after you create these .v files, you just run these commands, and then the output should show in the terminal. After you run it, add comments to this code showing me that you understand what each part of this lab is doing. Run these commands. No need to run GTK wave because the output should show in the terminal, and submit that with a screenshot, and then after that you can submit your report. Okay, now before we actually get, well, there's actually one thing I want to say. So all of this code for the MIPS data path, I actually can't take credit for this. So this is actually taken from the lab manual that was provided to me by Professor Gomez. So Professor Gomez was actually the professor that was teaching computer architecture before I started teaching it. He's actually my advisor. And all of the code was actually taken from this. So before we actually start running this thing, you do need to have an impression of what this code is doing so that you can write the appropriate comments for your lab report. Okay, so give me one moment and I will go ahead and started explaining what each component of this data path does. Okay, so let's get started. So let's start with some of the stuff that we already know. So if you have a program which may be written in any language you want, it could be C++, C, JavaScript, anything, right? So if you have a program that's written in C, it gets converted using an assembler to assembly code. And that assembly code is then converted by a compiler to machine code, right? So for a C program, you could see lines of code that might look like this, like C out, hello world, like that. Assembly code looks more like something like this, like add $sign S1, $sign S2, $sign S3. This is what assembly code might look like. And then machine code, you already know what that looks like. It just looks like zeros and ones, right? Like 0, 1, 1, 0, 1, 0, so on and so forth. So this is a brief look at what it looks like. So when the program gets converted all the way to machine code, those lines of machine code, there's going to be like billions of lines of machine code, right? All of this machine code is going to be stored into this circuit here. This is called the instruction memory circuit, okay? So if this rectangle here represents the instruction memory circuit, so I'm just gonna write some random lines of machine code here. So while all this is here, we have another circuit called PC, which stands for program counter. So program counter. And the way that this works is that program counter contains the memory address of the next instruction. So depending on the memory address that it's pointing to, it could be pointing to this first line of machine code here. When it's time to move on to the next line of machine code, it goes on to the next one here, the next one here, so on and so forth, okay? And the way that this works is that the memory address here, it gets incremented whenever it's time to move on to the next set of instructions, okay? So that's the way that this works. What happens next is that what happens next completely depends on what type of instruction that we're looking at. So far we've covered this part of the circuit, but what happens in the next part of the circuit, like all of this, completely depends on what kind of instruction we might be looking at. And as you already know, when it comes to computer architecture, well, at least for when it comes to the MIPS data path, there are 3 types of instructions. There's R-type instructions, there's R-format instructions, there's I-format instructions, and then there's J-format instructions. Okay, so depending on what I'm looking at, like a bunch of different things might happen. So let's say, I'm going to erase all this for now. Okay, let's say that the instruction that I just happened to be looking at, maybe this one here, happens to be an R format instruction. So basically what R format does is that R stands for register. So basically all of the, we're manipulating all of the data that's stored into the inside of the registers. So you see this circuit here that contains our registers. This register circuit contains 32 bit registers. Okay? So one register could contain some value. The next register could contain some value. So on and so forth, right? So let's say that the instruction that we might be looking at would probably be add $S1, $S2, $S3. This basically says take the value that's in register S2, add it to register S3, and then store that value into register S1. You know, that's basically what that's doing. So depending on what is in the what line of machine code is being done, this is we will manipulate what's in the registers if we're dealing with an R type for instruction. Okay. Let's say that we were dealing with an I type instruction. Okay. So what's the difference between R type instructions and I type instructions? Well, I type instructions, there's only two types of I type instructions. There's stores and there's loads. Okay. So basically what this does is that, because we only have 32 registers, we can't possibly store every variable that we're going to use into the registers since we only have 32 of them, right? So the reason why we have a circuit here called data memory is so that we can store variables that we don't need yet into memory and then put them in the registers later when we're ready to use them. Okay? So if we are moving information from the registers to the data memory, this is called a store. If we're moving memory, or if we're moving values from the data memory to the registers, this is called a load. Okay? So if we were dealing with an I-type format, then both this circuit and this circuit would be the ones that are being used, right? After that, we should also start talking about what happens when we see a J-type format, okay? So what type of commands encompass J-type format? There's really only the only types of commands that are J-type format are the ones that use jumps or labels. Kind of like if the C program that we converted to assembly code might have user-defined functions that will jump back and forth, where control is being shifted from the main program to user-defined functions, right? So and that's not the only situation in which J format instructions are being used. They're also being used in loops as well. So any kind of situation where we need to utilize a jump in order to perform the variables that we're trying to do. Okay. So that's basically what's happening in this diagram. So one thing that's very important is, how does the MIPS data path know when we're dealing with R-type format, I-type format, or J-type format instructions, right? So the way that it knows is that there's a control unit present. So let me go back to the pen real quick. So you see this control unit here. It's outlined in yellow here, okay? So the control unit analyzes the instruction that's currently being performed. It looks at the opcode of that instruction, and it uses that to determine whether the instruction is R format, I format, or J format. And if it's depending on what it sees, it's going to send signals to this multiplexer, and this multiplexer, which will direct the flow of data. So If we were dealing with an R-type instruction, we would really be only concerned with changing the values in the registers circuits, and we wouldn't really be touching the data memory circuit at all, right? So these multiplexers, because they're decision-making circuits, they choose which circuits get interacted with. Okay? So these multiplexers, they take in several inputs. And this is something that you've learned before, like in Lab 4. So the way that a multiplexer works, I can draw something better than this. The way that a multiplexer works is that it takes 2 to the n input signals. It has n selection wires and has 1 output wire. Okay? So in this case, for these 3 multiplexers that I circled here, there's only 2 wires that they're choosing from, right? So here, let's call this wire 1. There's a wire 2. So because there's 2 to the power of 1 is equal to 2, so n would be equal to 1, so there's only 1 selection wire. And then we have 1 output here, right? So selection could be equal to, if selection was equal to 0, for instance, output would be equal to whatever wire 1 is. If selection was, however, equal to 1, output here would be equal to whatever wire 2 is. It's a decision-making circuit, right? So by implementing the multiplexers here in strategic locations, we can decide which circuits get interacted with and which ones don't. Okay? And there's other parts of this circuit that's being implemented here. I mean, this is an addition circuit. This is an ALU. This is a sign extend circuit for I-type instructions, but I'm not going to go too far into that. That's basically what's happening here, okay? So keep in mind that every time a clock cycle happens, so every time a clock cycle happens in your computer, this MIPS data path is performing one of the instructions that's being stored in its instruction memory circuit. Okay. So, for instance, let me go ahead and erase this again. Okay. So, let's say that. Well, here's what I'm going to do. I'm going to open my task manager and I'm going to show you what my clock speed looks like. So this is the clock speed of my computer. It's 3.33 gigahertz. So that means that my computer, I'm going to write this down. So 3.33 gigahertz. This means that it's performing 3.33 times 10 to the 9 clock cycles every 1 second, right? So, depending on how many clock cycles is required per instruction, that's how many times that this data path is doing a full circuit, okay? So let's say that in order to perform an instruction, maybe one instruction requires, and this is just an example, let's say one instruction requires 1.5 clock cycles. That means that this, and let's say that the program that I'm using, that I converted from C to assembly code and then assembly code to machine code, it has maybe and I'm just making this up as an example. Let's say that it has 500 500,000 instructions, right? Let's say the program that I'm looking at has 500,000 instructions. How much time would it take? How much time would it take for this MIPS data path to execute this many instructions? Well, let's find out. Scroll down. Can I scroll down? No, I can't. Okay, I'm gonna have to erase this. Okay, so assuming that the program that we want to execute has 500,000 instructions, and it would take this many clock cycles. So it takes this many clock cycles per instruction. So that means our program needs 500,000 instructions over 1, and we would be performing 1.5 clock cycles per 1 instruction. In order to convert this into time it takes, we would just take our clock speed and we would take the inverse of this, right? So I would put 3.33 times 10 to the 9 clock cycles per 1 second. And this is the math that I would have to do some math here. So 500,000 times 1.5 divided by 3.33 times 10 to the 9. This would give me, this would result in 2.25 times 10 to the negative 4 seconds. This translates to 0.0000225 seconds. So if we had a program that was converted from C code to assembly code, and then assembly code to machine code, and if that machine code just happened to have 500,000 instructions, if my processor was using a MIPS data path here, and assuming that it takes 1.5 clock cycles per 1 instruction, in order for me to execute that program, it would take 0.000225 seconds to execute. So that means that the number of, so ignoring this part here and just focusing on the number of clock cycles here, 500,000 times 1.5, this is going to be equal to 750,000. So 750,000 clock cycles was required to finish this program. And because we have one instruction happening every 1.5 clock cycles, that means that every 3 clock cycles, 2 instructions are happening. So every clock cycle, every 3 clock cycles, this is looping once and then twice every time we need to do this. And keep in mind that this circuit is doing this work tremendously fast. Like, it did this many instructions in this amount of time. So it's pretty astounding what the kind of work that's being done inside your processor. If it was built using a MIPS data structure. Okay, so I think that's a good enough explanation of what's happening here. I think this example that I provided touches on more or less everything that we discussed in chapters 1 through 4, right? So now that you have a good amount of context, I think we can go ahead and start looking at the lab now. So you're gonna need to put comments explaining what each part does. So this here is a multiplexer. So the way that this works is that it takes two input wires. Both of them are, there are two 32-bit input wires. Okay. So maybe I'll make a drawing here. So the way that this multiplexer works is that you have you have a multiplexer that looks like this. You have two 32-bit input wires. One is called A, the other one is called B. And you also have a selection wire that's 1 bit, right? And you also have an output wire here that's also a 32-bit wire. It's called Y, okay? So if you look in the bottom here, this is our ternary operator. So Y is going to be set equal to either A or B, okay? So the way that we determine that is that we check to see what the selection wire is equal to. If it was equal to 1 or true, Y would be equal to whatever A is. So if selection was equal to 1, Y would be equal to A. However, this is what Y would be equal to if selection was not true. So if selection was equal to 0, this would result in Y being equal to B, okay? So that's the way that this multiplexer works. Then we have our incr.v. So the purpose of the incrementer.v is that if you recall what I said before, we have a circuit called program counter, which keeps track of which instruction inside of the instruction memory circuit that we're performing. So if we move on to the next memory address, which will contain the next command, it will execute that command and so on. So we need a way of incrementing program counter so that we can go on to the next instruction, okay? So that's actually the purpose of the incr.v. It contains a module called incrementer. Now, if we were actually building the circuits, we would be incrementing the incrementer by 4, right? And the reason why we would be incrementing by 4 is because, well, maybe I should draw it here. The reason why in real life we would be incrementing by 4 is because a 32-bit instruction looks like this, right? So it might have this instruction spans 32 bits, right? 32 bits is equal to 4 word sizes, right? Because a single word size is 8 bits, right? So 8 bits makes a word, 8 bits, 8 bits, 8 bits. So it would take 4 word sizes in order to fully encompass a 32-bit machine code, right? So let's say that we also had, say, another line of machine code underneath this. So this is also 32 bits. So if our PC was pointing at this, and we needed, which starts here, and we wanted to point in the next one, we would have to increment it by 4, which would mean that it's now pointing here, okay? This is because the memory address cells are always word size. So in real life, we would be incrementing this by 4 in order to get the next instruction. If you weren't incrementing this by 4, what would happen as a result is that instead of getting, neatly grabbing each instruction like this, let's say that you, for some reason, you decided to increment by 3 instead. And this is just an example, by the way. If you were incrementing by 3, what would happen as a result is that the bits that you would get for your instruction would be the last 8 bits of the previous instruction and the first 24 bits of the next instruction, and that wouldn't make sense, right? So if you were incrementing by 3, this is what would happen, and this wouldn't make sense. So we would have to increment by 4 each time, because 4 word sizes makes a 32-bit machine code instruction, okay? But because what we're writing here in Verilog is just a representation of a MIPS data path and not an actual MIPS data path, we have to be practical here and just increment it by 1. But ideally, we would increment it by 4. Just throwing that out to you here. Okay, and then after that, we have our mem.v. Let me go back to the instructions or the diagram here. So our mem.v represents our data memory. So this is being, So when it comes to our mem.v, this is what's being interacted with whenever we perform an I-type instruction. Okay? So the way that this works is that we have memory cells we have memory inside of computer, and memory is just a very long array of memory addresses, and each address can contain a value in it, right? So depending on how much memory you have on your computer, your memory could be very large. But because this is a kind of a short scale version of our memory, we only have, say, this example here only has 10 different memory cells, right? But in real life, how many memory cells would your computer have? Probably millions, right? But for this example, we only have 10. Okay? Okay, so moving on here, this is our PC mod.v. So as an example, in order for me to explain what's going on in this circuit, let me go back to the diagram. So the purpose of PC, which is the program counter, is that it points to the next instruction that needs to be performed in the instruction memory cell, okay? So what happens with PC is that it's being incremented each time, right? So this is the circuit here. So keep in mind that this isn't my code. This is the code that was provided to me by my previous instructor. So I would be lying if I said I knew exactly what each thing that was happening inside of the circuit. But basically, remember, the PC is keeping track of which instruction it's pointing to in the next part, okay? And then if ID, so now you have a module called if ID. So the way that this part works is that I believe the way that the circuit works is that it's part of the decision-making process. It determines if the instruction that we're looking at might be an R-type instruction, which stands for register, or I-type instruction. Okay? Yeah, I think that's what's going on here. Though I'm not entirely sure. Okay, so ifetch.v. So the purpose of this is to bring all of these different modules together. So inside of this ifetch.v, we include our multiplexer, our memory, our incrementer, our ifid, our PC mod. And the way that this works is that we have instantiations of each one. So let me zoom in a little bit. Okay, so let's see. So the way that this works is that as you can see here in our ifetch.v, we declare an instance of the ifetch module, which is declared in one of the previous slides. No, actually, scratch that. We're defining it here. So ifetch has two output wires of both of them being 32 bits. We have one input wire, which is 1 bit, and one input wire, which is also 32 bits. And then we declare a couple other wires here. We have a wire called PC, which stands for program counter, which is a 32-bit signal. We have our data out, which is also a 32-bit signal. We have NPC and NPC mux, which are also 32-bit signals. After we declare these, we then use the wires that we have here to begin constructing our circuit. Okay, so so over here we declare an instantiation of the multiplexer, our mux, which is all the way up here. We declare an instance of this. Remember, mux requires 3 inputs. No. Yeah, 3 inputs and 1 output. 2 32-bit inputs, a 1-bit input, and a 1 32-bit output. Okay? So if I scroll back down here, we put them in order here. So we put so this here represents the first input, the second input, our selection input, and whatever our output wire here. And then we declare an instance of our program counter. So we say the name of our module, the variable, which we call it PC mod 1, and here are the 2 wires, right? So let me quickly go back to the program counter module. So pc.mod. So pc.mod requires 2 wires, an input wire, which is 32-bit, and an output wire, that is 32-bit. And the way that this works is that PC is incrementing each time a clock cycle happens. So let me go back down here. Okay. So we feed these. So this is our input, this is our output. After that, we declare an instance of our memory circuit. So the name of our circuit is called memory, and the variable name we assigned it to it is called memory1. So let me go back to our memory.v circuit. So it requires 2 inputs here, okay? One output wire that is 32 bits and one input wire that is also 32 bits. And the wires that we assigned to it are these 2 wires here. And then we have our if ID. So let me go back to this module here. If ID requires 2 32-bit outputs and 2 32-bit inputs, okay? And we assign them here, okay? And then we have our incrementer. We feed these wires to it. So basically, this hooks up our entire circuit. So I don't know if I need to actually like draw this out so that you have a better understanding. Let me see if I can. So we have a multiplexer here. Which takes 2 32-bit inputs, an output, and a selection wire here. So for the inputs, we have so the wires that we're giving as the inputs are our A wire. We're going to feed the wire that we call EX mem NPC, which is declared over here. So this is EX mem NPC. The second input is called NPC. Our selection wire is called EX mem PC source. And then our output wire is going to be Y, which is NPC mux. Okay. After that, we have our PC mod, which takes a 32-bit input and a 32-bit output. So the input is going to be called our PC wire, which we declared here, and our output wire is called .npc mux. So excuse me, it takes 2 inputs, my bad. So because the input is going to be npc mux, the output of the multiplexer is going to be one of the inputs for the PC mod, okay? And then when it comes to memory, it takes 2 inputs, I believe. Yeah, 2 inputs, no. 1 input, which is 32 bits, and 1 output, which is 32 bits. So the input wire is called ADDR, and the output is called data. So if I keep drawing this out, so we have memory. It has 1 input called ADDR, which is our PC, and 1 output called memory. Well, I'm actually not going to draw this out because I think you guys get the point of what this is doing. And also, you also have the circuit diagram here, okay? Which is, so this code is roughly emulating what this circuit is doing. So I think what you want to see now, I'm not going to waste any more time. I think what you want to see now is me putting this all together, okay? Okay, so over here I have my Lab6A folder. So what you need to do is create a new .v file for each of the 7 .v files that you need. Over here, this is my ifid.v. This is my ifetch.v. This is my increment.v. This is my memory.v. This is my multiplexer.v. PCMod.v. And then pipeline is kind of like my test bench here, okay? So, copying these instructions, open Visual Studio Code, create each of the 7 files as listed, add comments, code with no comments gets no credit. And I think I already explained what each component of the circuit's doing, right? So all that's left to do is after you get these 7 files into your Visual Studio Code, we just have to run these commands here. So I'm going to say iverilog -o pipeline.vvp pipeline.v. So this creates our VVP file. Next we say vvp pipeline.vvp. And after that, we have this output here, okay? So the way that this program works is that it's not putting the signals in GTK wave, okay? Instead it's outputting them here. So what you gotta do is after you get this to work and you get this output here, all you gotta do is take a screenshot of this, add this to your lab reports. So what you're going to need for your lab report is that you're going to need a brief paragraph explaining what each component of this circuit is doing. You're going to need to attach the source code with comments, and then you're going to need the screenshot from the terminal, and that will be your Lab6. Okay? Now, I don't expect you to fully understand what's happening inside of this inside of this code. I don't even completely understand what's going on in this code, but yeah, this was the code provided to me by my previous professor showing how to emulate the MIPS data path in Verilog, okay? So if you have questions about this lab or any of the other labs, I am available. Please reach out to me via email or Discord, and yeah, thank you for watching this video. This is the last lab for computer architecture.